You are trying to find the derivative of the function f(x is equals to x squared. During the process, you eventually reach a point where you have the expression 2x plus h, and of course your answer will turn out to be 2x. That is, according to both Newton and Cauchy. For centuries this has been believed to be true, but as I'm about to show you, this is not actually correct. The story begins more than 2,000 years ago. In ancient Greece, mathematics was dominated by geometry. Among the greatest mathematicians of that era was Archimedes. Archimedes wanted to answer a deceptively simple question: what is the area of a circle? The difficulty is that circles have no straight edges. Greek geometry relied on straight constructions, so Archimedes invented a clever workaround. He approximated the circle using polygons. First a hexagon, then a 12-sided polygon, then 24 sides, 48 sides, 96. Each step brought the polygon closer to the circle. This became known as the method of exhaustion. By pushing this method far enough, Archimedes calculated a remarkably accurate value of pi, but something deeper was happening. Archimedes was approaching the idea of a limit. He just didn't formalize it. And that hesitation would slow mathematics for nearly 2,000 years. If Archimedes was already so close to the idea of limits, why didn't the Greeks invent calculus? The answer lies in their fear of infinity. Greek philosophers believed infinity was philosophically dangerous. Allowing infinite processes in mathematics raised troubling questions. If something can be divided infinitely, does it ever end? And if it never ends, can it be measured? These philosophical concerns prevented Greek mathematicians from fully embracing infinite reasoning. So despite Archimedes' brilliance, the concept of calculus remained just out of reach for centuries. At the same time, philosophers were struggling with the concept of motion. One famous puzzle came from the Greek philosopher Zeno. Imagine an arrow flying through the air. At a single instant, the arrow occupies a specific position. At that instant, it isn't changing position. So at that instant, it isn't moving. But time is made of instants. So if the arrow isn't moving at any instant, how can it ever move? This puzzle became known as Zeno's paradox of motion. It reveals something profound. Our intuitive idea of motion doesn't match the mathematics available at the time. To solve the paradox, mathematicians needed a new language, a language for continuous change. That language wouldn't appear for almost 2,000 years. In the 1600s, science began to transform. Astronomers were studying planetary motion. Physicists were studying falling objects, but describing curved motion mathematically was extremely difficult. One scientist trying to solve this problem was Johannes Kepler. Kepler discovered that planets move in elliptical orbits, but calculating areas and volumes of curved shapes remained challenging. While studying wine barrels, Kepler even approximated volumes using extremely thin slices. The idea worked surprisingly well, but it raised a troubling question. How thin could those slices be? Could they become infinitely thin? That idea would soon lead to a mathematical revolution. In 1635, mathematician Bonaventura Cavalieri proposed a radical idea. He suggested that geometrical shapes could be treated as collections of infinitely thin pieces. He called this method the method of indivisibles. Imagine a plane shape made from infinitely many parallel lines, or a solid made from infinitely many planes. By comparing these infinite collections, Cavalieri could calculate areas and volumes. It worked beautifully, but critics immediately raised objections. What exactly are these infinitely thin objects? Are they numbers? Are they geometric objects? Or are they something else entirely? No one could answer clearly. Still, mathematicians kept using the idea because it worked. And then in the late 1600s, two mathematicians independently discovered the mathematical framework that would transform science forever. The two men were Isaac Newton and Gottfried Wilhelm Leibniz. Both invented calculus, but they approached it in very different ways. In 1665, a plague outbreak forced Cambridge University to close. Newton returned home. During this period of isolation, he began developing new mathematical ideas. Newton focused on motion. He described change in quantities as fluents. Their rates of change were called fluxions. This allowed him to describe motion mathematically. Years later, he used those ideas in his great work, Philosophiae Naturalis Principia Mathematica. There he derived the laws of motion and universal gravitation, but Newton rarely published quickly. Many of his discoveries circulated privately in manuscripts, and that delay would soon cause a major controversy. Meanwhile, in continental Europe, Gottfried Wilhelm Leibniz was developing his own approach. Leibniz emphasized symbolic notation. He introduced two symbols still used today, dy over ds for derivatives and the elongated s for integrals. In 1684, he published his discovery in Nova Methodos Pro Maximis et Minimis. This was the first published paper on calculus. Leibniz's notation turned out to be extremely powerful, and it quickly spread across Europe. But instead of celebrating the discovery, mathematicians soon found themselves in a bitter dispute. Supporters of Newton accused Leibniz of plagiarism. The dispute escalated. Eventually, the Royal Society investigated. In 1712, the Society issued a report concluding Newton invented calculus first, but historians later discovered something remarkable. Newton secretly wrote the report himself. Today, historians agree that Newton and Leibniz developed calculus independently, but while mathematicians were arguing about priority, a deeper problem was emerging. Early calculus relied on infinitesimals, extremely small quantities, smaller than any ordinary number but not exactly zero. For example, suppose y is equals to x squared and a small change dx produces y plus dy is equal to x plus dx, all put into brackets and squared. Expanding gives x squared plus 2x dx plus dx squared. Subtract x squared and you get dy is equals to 2x dx plus dx squared. Divide by dx and you get dy over dx is equals to 2x plus dx. Then mathematicians simply dropped the dx. Dy over dx was then equal to 2x. But this raised a troubling question. What exactly is dx? If it equals 0, division by 0 is impossible. If it does not equal 0, we cannot ignore it. For decades, mathematicians quietly overlooked this contradiction until one philosopher decided to challenge it. In 1734, philosopher George Berkeley published The Analyst. His criticism was devastating. He argued that infinitesimals were logically inconsistent. Mathematicians treated them as non-zero when dividing by them, then they treated them as zero when discarding them. He famously called them ghosts of departed quantities. For mathematicians, this was embarrassing. Yet calculus continued producing correct predictions in physics and astronomy. For more than a century, calculus remained both indispensable and philosophically uncertain. In the 19th century, mathematicians finally resolved the crisis, or at least they believe they did. Key figures included Augustin Louis Cauchy, Carl Weierstrass, and Bernard Riemann. They rebuilt calculus using limits. Instead of infinitesimals, derivatives were defined as of x plus h minus f of x all over h, that is, as h approaches 0. Here h never becomes 0. Instead, we examine what happens as it approaches 0. Weierstrass later formalized this idea using the epsilon delta definition of limits. For the first time, calculus had a rigorous logical foundation. And again, at least they believed. It seemed the story was finished. Infinitesimals had been eliminated. But in 1960, mathematician Abraham Robinson developed non-standard analysis. He constructed a number system called the hyperreal numbers. These numbers include genuine infinitesimals. Within this framework, The original reasoning of Leibniz becomes mathematically rigorous. The ghosts of departed quantities turned out to be mathematically possible after all. Or did they? Have you ever wondered why the limit definition doesn't naturally click? How it doesn't naturally align with intuition? Here's the thing. Though the definition is logically sound, such that one can later grasp it, the problem is that beneath all that flawless logic lies the brainchild of Zeno, the idea of approaching something, but never actually reaching it. An idea that was openly rejected in physics is now implicitly embraced in mathematics. But mathematics is the language of physics, and that can only mean one thing. Physics is secretly dancing with Achilles. Now, it's not that calculus is wrong. Newton and Leibniz discovered something remarkable. However, mathematics as we have it just falls short of fully expressing it. Calculus in its essence derives from the physical world, and not from math, and consequently a more meaningful formulation of it comes from a correct understanding of physics. What Weierstrass and Robinson essentially did was create abstract mathematical objects that allow for the veiling of Newton and Leibniz's illogical computations so that one can arrive at the answer without the guilt of using inconsistent math. But that is just one thing. Another problem is that the derivative of y is equal to x squared isn't actually 2x. 2x is just an excellent approximation. The correct answer takes the form of 2x minus 1, which comes from the following computation. Y is equal to x squared. Let y equal to f of x. The derivative of f of x is equal to f of x minus f of x minus change in x. And we get x squared minus bracket x minus change in x bracket all squared, which brings us to x squared minus bracket x squared minus 2x change in x plus bracket change in x bracket squared closed bracket, which gives us x squared minus x squared plus 2x change in x minus bracket change in x closed bracket squared, which gives us 2x change in x minus bracket change in x bracket squared. And after all this, we get 2x minus 1 is the correct and final answer. But at first glance, 2x is not approximately equal to 2x minus 1. The thing is, the approximation kicks in at large measurement scales, e.g., x is equal to 1 million units. 2x is not approximately equal to 2x minus 1 when working at quantum scales. What breaks down is our familiar form of calculus, not the one I'm introducing to you. The latter is derived from reality at these very scales, that is, the quantum scale. The mathematics of calculus I'm introducing to you probably carries an unfamiliar form, but this is its natural or its more natural form, the one that is not subject to all the problems I previously pointed to in the former form. In order to truly understand this new form, one has to truly understand S is equal to ut plus half a bracket t squared plus t close bracket. But that's for another time. Mr. Berkeley. What? The ghosts are back.